integral 0 to 2 pi d theta upon 1 minus 2a sin theta plus a square, where 0 less than a less than 1. We have the given integral of the type integral 0 to 2 pi f of cos theta sin theta d theta, where f of cos theta sin theta is a rational function of cos theta and sin theta, given by 1 by 1 minus 2a sin theta plus a square. Here, term containing cos theta is absent. We can make use of z equals e raised to I theta. Substitution. From where we have relations sin theta equals z minus z inverse upon 2i and d theta equals dz upon iz. So that the given integral can be rewritten as integral over c dz upon iz divided by 1 minus 2a into 1 by 2i into z minus 1 by z plus a square. 2 and 2 gets cancelled and we take LCM in the denominator. We obtain the common denominator as iz. This iz after taking LCM can be cancelled with the iz which appear in the numerator. We have the simplified form obtained as negative integral c dz upon az square minus I times a square plus 1 into z minus a, which is quadratic in z. We have the linear factors obtained as az minus I into z minus ia, where c is the unit circle. If you suppose f of z equals 1 by az minus I into z minus ia, in order to evaluate poles, we will equate denominator to 0, and we have the poles obtained as z equals I by a and z equals ia. Suppose z1 equals I by a, and when you evaluate modulus, we have modulus I by a is greater than 1, because 0 less than a less than 1 is given, and hence we have 1 by a is strictly greater than 1. Because of that reason, even if modulus I equals 1, we have modulus I by a will be greater than 1, and hence we have z1 equals I by a will lie outside the unit circle. Now we will evaluate modulus of z2, where z2 equals ia. Modulus of ia is strictly less than 1, because modulus I equals 1 and we have a is less than 1. Therefore, modulus ia is strictly less than 1, and hence z2 will lie inside the unit circle. Now we will have to evaluate residue of f of z at z2. We have limit z tends to ia, z minus ia into f of z obtained as limit z tends to ia applied on 1 by az minus I. By direct application of limits, we have residue of f of z at z equals ia obtained as 1 by I times 1 by a square minus 1. By residue theorem, we have integral over c f of z dz equals 2 pi I into sum of residues, but one of the poles only lie inside the unit circle. Therefore, we have 2 pi I multiplied to 1 by I a square minus 1, which equals 2 pi upon a square minus 1. By equation 1, we have the given integral takes the value negative integral over c f of z dz. Hence, we have the final answer obtained as 2 pi divided by negative 1 into a square minus 1, which becomes 2 pi upon 1 minus a square.